Hello everybody! In this video we'll continue our learning about reactions with aldehydes and ketones. And this video is about the formation of hemiacetals and hemiketals. So hemiacetals are molecules where we have a carbon, we have an R group, a hydrogen, an alcohol, and then an alkoxy group. So an oxygen bonded to another carbon chain. A hemiketal is almost the same except for we have two R groups bonded directly to the carbon as opposed to an R group and a hydrogen. And then we still have an OH and then an alkoxy group, oxygen with another carbon chain. The prime here, that apostrophe after each R, is just to say that let's say if we're focusing on these two groups right here, they could be different from each other. They don't have to be the same R group. Same thing here. So one could be a methyl, one could be a propyl, one could be a butyl. They could also all be the same. It just doesn't necessarily have to all be the same. So that's all that prime indicates. And before we get into the mechanism to form these, let's talk about an application in biology or biochemistry. So if we look at open chain glucose, we'll ignore stereochemistry for a second here, but open chain glucose, which exists in pretty low concentrations at equilibrium. It's a 6-carbon chain, just like how cyclic glucose is a 6-carbon ring. Bunch of alcohol groups bonded to each carbon, and there is an aldehyde as well. The cyclic form of glucose is formed through a reaction that is the same mechanism as how we form a hemiacetal. So cyclic glucose is a hemiacetal. This open chain glucose we can also draw similar to a cyclohexane ring, but we won't show that connection yet. We're just going to orient the atoms so that it's easier to see where the atoms bond to form a cyclic ring, but this will still be the open chain glucose. Looking at it, just arranging the atoms to look more like a cyclic carbon. So we have the aldehyde on one side, the alcohol on the other side, and then each carbon in the ring is also bonded to an OH group. And you notice all of these are in the equatorial position, all of the OH groups. Might remember that from previous classes, that atoms or substituents in a cyclohexane ring in the equatorial position is more stable than axial positions. Okay, so open chain glucose in a solution with water and an acid or a base present, and there is usually some acid or base present, the open chain glucose will undergo a reaction to form a hemiacetal. And this is not the entire mechanism, but just to kind of guide where you're looking here, when we close the ring, we have this oxygen, the OH group at the end of the chain, will create a bond to the carbon that's part of the aldehyde. So the cyclic form of glucose, we have a 6-membered ring. The oxygen at the end of the ring that was an OH group is now just an oxygen. It doesn't have a hydrogen bonded to it. The aldehyde oxygen becomes an OH, and this can be formed with different stereochemistry, axial or equatorial, so we're keeping it ambiguous with that squiggly line. And then all the other alcohol groups are still present. So this is now the cyclic form of glucose. This is a hemiacetal. Now we said a hemiacetal has an OH group, an R group, and a hydrogen, and an alkoxy group. Well, this carbon that I'm drawing out in purple right there, I'll zoom in here. This carbon is bonded to an OH group. This area and beyond is the OR group. Pick a different color. Over here we have an R, the carbon, and then the hydrogen is implied but not shown, but there's also a hydrogen bonded to that carbon. So here's the very basic way that we go from a open chain glucose to a cyclic form of glucose, and that cyclic form of glucose is a hemiacetal. So now let's write the reaction scheme for forming hemiacetals and hemiketals. We'll draw each reaction scheme separately. Now, we're in our aldehyde and ketone unit. If we start with an aldehyde and we add an alcohol, for this reaction scheme, we'll draw ethanol. Then we have an acid or base present in solution. These reagents can form a hemiacetal. Hemiacetal, we have carbonyl carbon bonded to its hydrogen, bonded to the R group from the original aldehyde. The carbonyl oxygen becomes an OH group, and then the other alcohol present in solution bonds to the carbonyl carbon without the alcohol hydrogen. So we can trace these atoms here. That alcohol is now bonded to that carbonyl carbon. The reaction mechanism, reaction scheme is very similar if we start with a ketone. Before we do that, let's just label everything. Over here we start with an aldehyde and we form a hemiacetal. And then if we start with a ketone, with the same reagents, we have some alcohol. Here I'll show ethanol. We have an acid or a base present. So these are acid or base catalyzed reactions, reversible reaction. We form a hemiketal, so carbonyl carbon in the center there, still bonded to the two R groups from the ketone. The carbonyl oxygen becomes an OH group, and then the oxygen and carbon chain from the alcohol is bonded to what was the carbonyl carbon. And this is a hemiketal. So two reaction schemes. These are two separate schemes. They're separated by that vertical dashed line there. One shows the reaction scheme to form a hemiacetal, starting with an aldehyde, and the other shows formation of a hemiketal, starting with a ketone. Now let's go through the mechanism. We'll do the mechanism for a hemiketal, but it's the same mechanism if you're starting with an aldehyde or a ketone. We just get a different product because of the hydrogen that's present in an aldehyde, not present in the ketone. This mechanism is analogous to the hydration mechanism that we've done in a previous video. And you might recall we can do hydration reactions acid catalyzed or base catalyzed, so with an acid present or a base present. That's also true for these reactions, formation of a hemiacetal or hemiketal. And we'll show here the acid catalyzed mechanism. So it's analogous to hydration. You'll see very similar steps, and we'll do acid catalyzed. So if there is an acid present in solution, often in these reactions as well, that alcohol that's added, so in the reaction schemes above the ethanol, that would be the solvent that the reaction happens in. So you're adding some aldehyde and some acid or some base to a solution of ethanol. So if we're adding the acid, we're doing an acid catalyzed mechanism, then we have the neutral alcohol molecule present in solution in equilibrium with the protonated version of the alcohol. So these are the molecules present in solution, kind of similar to when we did the hydration reaction. These are the molecules that will be used to carry the reaction forward. We have both of these in excess, so we can use them as needed for each step of the mechanism. And just to be clear, if you're thinking, where did the second hydrogen come from for that protonated alcohol? Remember, we added acid to solution. So with acid present, there are abundant hydrogen cations, abundant protons. So a neutral alcohol molecule can then bond to an acid or an acidic hydrogen. So this will always be this first step to determine what is present in solution as far as the solvent goes, and if it's acid catalyzed, we have protonated alcohol. If it's base catalyzed, we have deprotonated alcohol present. Okay, so now we're doing a nucleophilic addition reaction to a ketone. So if we start with a ketone in acidic solution, the ketone will start by getting protonated and thus activated by the acidic version of, or the protonated version of the solvent. So oxygen electrons pull a proton from protonated solvent, and the electrons in that oxygen to hydrogen bond will go to the oxygen. Now we have our activated ketone, our activated carbonyl. Oxygen is bonded to a hydrogen. That protonated oxygen is pulling electron density stronger away from that carbonyl carbon, and so that makes that carbonyl carbon more susceptible to nucleophilic addition. So if we're adding a nucleophile to that carbonyl carbon, we have protonated solvent and not protonated solvent present in solution. While the neutral solvent is a better nucleophile, those electrons are much more available. So the neutral version of the solvent will act as a nucleophile, bond to the carbonyl carbon, and electrons from that pi bond will be owned by oxygen. So if we draw the product of this, starting with the bonds present from the ketone, we have carbonyl carbon bonded to the two methyl groups. The carbonyl oxygen now became an OH group. It has a single bond to the oxygen. And now we have the alcohol molecule bonded to that carbonyl carbon. We have a positive charge on that oxygen because it lost ownership of that pair of electrons. It's now sharing them. And so in this last step, really all that's needed is to deprotonate that oxygen at the bottom of the molecule. So we can deprotonate with neutral solvent. Oxygen electrons bond to hydrogen. Electrons from the oxygen to hydrogen bond are going to be owned by oxygen. Simple proton transfer reaction. And then now we've got our hemiketal product. And that's our mechanism there. Now I noted earlier that cyclic glucose is formed through a reaction to form a hemiacetal. These intramolecular hemiacetal, hemiketal reactions are favorable if you're forming a 5 or 6 membered ring. So let's just add this note. Intramolecular hemiacetal, hemiketal reactions to form 5 or 6 membered rings are favorable. So if you had a molecule like this one here, we have an alcohol group, we have 5 carbons, and then our aldehyde. If we count these carbons, we've got 1, 2, 3, 4, 5. Now this isn't the complete reaction, but just to simplify, or the complete mechanism, I should say, you can imagine that this oxygen from the alcohol group could bond to that carbonyl carbon, act as a nucleophile. Electrons from that double bond go up to the oxygen. We will have protonation, deprotonation steps as well. And then if we form the product, so this is an intramolecular reaction, now the product is a 6-membered ring with the oxygen as one of the members of the ring. And the oxygen is bonded to what was the carbonyl carbon and is now bonded to that oxygen. So if we number everything, with the pink arrows, we show the oxygen, which is after carbon 5, bonding to carbon 1. So here we have carbon 1, 2, 3, 4, 5. And this is a 6-membered ring. One of the members is an oxygen. This is a favorable reaction. 5 and 6-membered rings are quite stable, just like glucose. And just note that these mechanism arrows, they are simplified here. There are also deprotonation and protonation steps before we're actually getting to the final product. But just to make the point here that intramolecular reactions to form 5 and 6-membered rings are favorable.